Hello and welcome to this Python tutorial. In the previous tutorial we built two regressors, the linear regressor and the polynomial regressor. So this section is about polynomial regression, but we wanted to build this linear regressor as well to compare the polynomial regression results to this reference-based model here, which is the linear regression model. So we built those two models, and now we're going to visualize the results of both these models. And let's start by visualizing the linear regression results. Okay, so we're going to do exactly the same as what we did in linear regression, simple linear regression. We're going to start by plotting all the observation points. We have 10 of them. So that means that we're going to have the 10 levels on the x-axis and the 10 associated salaries on the y-axis. So these observation points will be the true results, that is the real salaries for the 10 different positions. And then of course we will build the predictions of our model. So first the predictions of the linear regression model and then the predictions of the polynomial regression model. And we will compare these true values, these true observations, to the predictions made by the model. So let's do this. Let's start by plotting the true observation points. As in linear regression, we're going to use plt.scatter. And in parentheses, remember we first need to input the x-coordinates, and the x-coordinates are of course the values in this matrix of features x, which actually has one independent variable, and that's why these are all the x-coordinates of our observation points, corresponding to the 10 levels of our observation points. So here we input x as the first argument, then comma, and then we need to input the y-coordinates of our observation points. And of course, these are going to be the real salaries, which are in this dependent variable vector y. So these are all the real salaries, and that's what we need to input for the y-coordinate. So y here. All right, then what do we need to input here? Maybe a color, because we want to make the distinction between the real observation points and the predictions made by our model. So let's add here a color, and we will choose the red color. So let's input it. Color equals red in quotes. Here we go. We did the job for the real observation points. And now let's plot the predictions. So the prediction, we're going to use plt.plot. And then remember, what do we need to input here? Well, first, that's the x-coordinates of our prediction points. So x here. But then, what do we need to input now for the y-coordinates? So yes, indeed, the second argument here is the vector containing the y-coordinates of our prediction points. And then what is this? These are going to be the predicted salaries predicted by our linear regression model of the 10 levels of this employee's previous company. So levels 1 to 10. And therefore we're going to take our object here that we created, that is this linear regression object, and therefore that is lin_reg. And then as usual we're going to use the predict method. So we need to add here a dot and then predict. All right, predict. And so, it's a method, so we add some parentheses. And according to you, what do we need to input in these parentheses? Well, since we want to predict the salaries of the 10 position levels, and since these 10 position levels are contained in the X matrix, well, it's a matrix of only one column, so this X column, therefore we need to input here X. Okay, and then the last argument that we can add to make a better plot is the color. So let's add the color here, same, and as I just explained, I'm going to choose a blue color for the predictions. All right, so now we plotted the real observation points and the predictions, that is the predicted salaries of the 10 position levels predicted by our linear regression model. Great, and now let's make an even more beautiful graph by adding a title. So here we add plt.title, and then which title would you like? Well, what about truth or bluff? This way, that definitely explains the situation. And let's also precise that we are plotting the linear regression results, because then we will make the same graph for the polynomial regression. Okay, and don't forget the quote here to close the title. All right, so that's done for the title, great. And now let's add a label to the x-axis. So it's plt.xLabel. All right, and here very simple, let's say position level. Okay, and now let's do the same for our y label, plt.ylabel, and then in parentheses, salary. Great, perfect. And let's not forget to add this plt.show to specify that the graph is ready and display it. Okay, so now let's have a look. Now it's the exciting part. It's the part where we have a look at the results. So let's do this. I'm selecting all the code section here and pressing Command and Control plus Enter to execute. And here we go. Let's enlarge the graph. Okay, so first of all, let's clearly make the distinction between the observation points that are the red points here, as you can see in red, and the predictions, which are the points on this straight line here in blue. So by the way, this is a straight line because that's the predictions of the linear regression model. And since of course the linear regression model is a linear model, then that makes a straight line as the fitting line. For a linear regression model, we will always have a straight line in 2 dimensions. Okay, so in red, real observation points, and in blue, predictions. Okay, so what can we interpret here? Well, first, these are not great predictions, except for this one here, where the red point is really close to its projected blue point on this blue straight line. And same for these points. Well, for the other points, we are quite far from the truth. Especially this one. Look, this one is really far from its prediction because, to get the prediction of a real observation point, what you have to do is to project this red observation point here on the line like this. And to get the predicted salary, you then need to project this projected point on the line onto the y-axis, which contains the salaries. So basically that means that for this observation points, the real salary is about $1 million per year. Well, that's actually a huge salary, but I think it's the CEO. Let's hope so. So let's say it's the CEO. If we want to look at the predicted salary of the CEO, well, we need to go back here on this red point, project it on this blue straight line here, which is actually our model, and then project it again on the y-axis containing the salaries. And then here we obtain that the predicted salary of the CEO is about $650,000 per year. So, if we were negotiating the salary with the CEO and using this model to predict if the CEO is bluffing, then the CEO would definitely be very unhappy. He would even be furious. Okay, so that's why we need to make a better model. Not to satisfy the CEO, but to, agree with the real observations, that is this red observations. Because as you can see, it's difficult to make a straight line that will be close to all these red points here. And that's why we need to level up and make a nonlinear model that will therefore not be a straight line here and that will make much better predictions, that is much better predicted salaries that will help us in our negotiation. And speaking of our negotiation, let's have a look at the 6.5 level here. So as we can see, the 6.5 level is around here. So to get the predicted salary of this 6.5 level, we need to project this 6.5 level on our blue straight line corresponding to our linear regression model, and then project it again on the y-axis containing the salaries, and we get around $300,000. Okay, $300,000. That means that if this employee hadn't said anything about its salary, we could have offered him $300,000 per year. And this employee would definitely have been very happy. But the HR team would definitely not have made a great job at optimizing the costs. Okay, so I hope now you're convinced that not only for the CEO, but also for our negotiation here, that we clearly need to make a better model to fit it better to our observation points, our position level and salaries. Okay, so let's now make this better model. So let's close this. And let's now visualize the polynomial regression results. So as usual, we're going to be efficient and copy all this. So I'm going to copy that and we're going to paste it here. And now let's see what we need to change. Okay, so first let's change the basics. We're going to replace here linear by polynomial. And then that's okay. That's okay as well. We want to keep the real observation points, but that is definitely not okay because these are the predictions of the salaries of the position levels predicted by our linear regression model. So here we need the predictions of our polynomial regression model. Okay, so what do you think we need to do? It's actually quite simple, but not that simple. I guess now what you must imagine is that we simply need to replace this linreg here by linreg2, right? That is what would actually come to mind naturally at first. But okay, let's see. Let's simply replace this linreg object by our linreg2, which is the object we created for our polynomial regression model. But as you can notice, this linreg2 object is actually not an object of a certain polynomial regression class. It's still an object from this linear regression class. So we actually need to add something here to get the predictions of our polynomial regression model. And what would be this something? If we go back to this section here, well, you notice that we actually first transformed the X matrix of features containing only the position levels into this X poly matrix of features containing not only the position levels, but also the polynomial terms of our independent variable containing the position levels. So remember X poly, where we can actually look at it. So this was the column of ones corresponding to the constant B0 in the multiple linear regression equation. And these are our position levels, and these are our polynomial terms of our position levels. Okay, so basically we transformed our matrix of features X into this matrix of features X poly containing the position levels. And we actually need to include that information here because right now what we're doing here is just to take a linear regressor object. So there is no polynomial features here. There is not any polynomial term. So instead of putting this matrix of features X here, without the polynomial term, we actually need to input this new matrix of features containing the polynomial features. And so what we have to do now is to input X poly here instead of X. But imagine we have a new X here. Well, since this X poly was already defined as the transformation of our matrix of features X, well, if we want to add some new observations here and plot some new polynomial regression results, we would rather take this polyreg fit transform here that transforms any matrix of features you want instead of X poly here. So that's why if I input this here, well, if you want to plot new polynomial regression results on some new matrix of features X, then what you only need to do is to replace X here, here, and here. So be careful not to fall in this trap. Don't use this X poly here because X poly was already defined for an existing matrix of features X, and we want to make this code here applicable to any new matrix of features X. And that generalizes well the visualization plot of the polynomial regression results, and therefore we have some very useful code here. Okay, and now the moment we are all waiting for. Let's see how the polynomial regression model fits better to our observation points, and let's find out what some nonlinear regression graphic results look like. So I'm going to select this code section here, and without waiting, let's find out about the polynomial regression results. And here it is. Let's enlarge this. All right, so that's the polynomial regression results. And the first thing I have to say here is that unlike what we're used to before, having a straight line fitting the observation points, now we don't have a straight line anymore. We have this curve here, which is due to the fact that the polynomial regression model is not a linear regression model. So a very important pillar of your intuition now is to make the distinction between linear models and nonlinear models. A linear model in 2 dimensions will give you a straight line, and the nonlinear model will give you anything but a straight line. So it can be a curve, it can be some very complex mathematical distributions, it can be anything you want but not a straight line. Okay, and now let's interpret the results. Let's start with the CEO, who was very furious last time with the linear regression model. So the CEO, as we said, has an annual salary of $1 million. Okay, great. And now what does the prediction of the polynomial regression say? Well, we need to project this red observation point corresponding to the CEO onto our blue curve here, which is the polynomial regression model itself, represented in 2D. And we need to project this point again to the y-axis containing the salaries. And we obtain a salary of $900,000. Much better than last time. And now let's look at the salary of our 6.5 position level. Okay, so I took the 6.5 level here, which I'm projecting on our blue curve, and then projecting it again on our y-axis containing the salaries, and we obtain a little more than $200,000. Better than last time. Remember, we obtained $300,000 with the linear regression model, and remember, this employee said that he earned an 160K salary in its previous company, so far this employee seems very honest, which is good. Oh, and by the way, of course, you can definitely see that this blue curve is approaching much better these real red observation points here than the linear regression model. Okay, but now we want to do even better. And to do this, we are going to add a degree to our polynomial regression model. And to do this, it's really simple. What we only need to do is replace this degree equals 2 here by 3. That way we're adding a degree, and now you're going to see if I execute this code section here that will build a new polynomial regression model, but this time with a 3 degree, you will see what we will obtain. So I'm going to press Command and Control plus Enter to execute, and new polynomial regression model created. Okay, so this time it has 3 degrees. So I'm going to select this and show you. Okay, as you can see, this is quite different from what we had before. Alright, so that's the polynomial regression model with a 3rd degree. So as you can see, it's not convex anymore. We have this first curve here and then a new curve here, which actually makes it not convex. And we can actually see that this blue curve is approaching even much better the red observation points than what we had before. Not only the linear regression model, of course, but the polynomial regression model with degree equals 2. And by the way, as you can see, the prediction of the CEO salary is now very close to the real observation, the real salary. And that's because our model is much better now. And same for our 6.5 level. If we project this 6.5 level now, we obtain actually a value that is close to what this employee gave as its previous salary. So that's actually really good for us and for the employee also, because maybe he'll get a bonus for honesty. And now, just for fun, let's look at the results we get if we add even one additional degree, that is a 4 degree to our polynomial regression model. So let's replace here degree equals 3 by 4. And now let's execute this. Done. And now let's have a look at the graph. I'm pretty sure that we will get now a perfect model predicting the 10 different position level salaries perfectly. So press Command and Control plus Enter to execute. And here we go. That's what I thought. Okay, let's enlarge this. Clearly now you can see that the blue curve is almost passing by all the red observation points here. And now we hit the bullseye for the CEO salary because, you know, the prediction is nearly the same as the real salary of $1 million. So we hit the bullseye for the CEO salary, and we can be pretty confident that we also hit the bullseye for our employee's previous salary that had level 6.5. And therefore, we're going to use this model, this polynomial regression model, because it seems to be really accurate to predict the salary associated to the 6.5 level using the predict method. But before we make that prediction in the next tutorial, we can notice that we can still improve this plot. Indeed, what's happening here is that our code is giving us the predictions of the model for each of the 10 levels from 1 to 10, but then it's plotting some straight lines in between the predictions. We can actually have the real continuous curve by, instead of having only the predictions from 1 to 10 incremented by 1, we can have the predictions from 1 to 10 incremented by a higher resolution, like a 0.1 step. So let's do this for those of you who want to have a more advanced plot, sacrificing some simplicity in the code. It's actually not that more complicated, you'll see. What we just need to do is to create a new X here that we'll call XGrid, and that will contain all the levels plus incremented steps between the levels with a resolution of 0.1. So to create this new X, it's really simple. We're going to use this arrange function from NP that gives a range from one bottom value to one top value. So here we need to specify the lower bound, which is min X, that is level 1, and the upper bound, which is max X, that is level 10. And now we choose the incrementation of 0.1. And this will give us a vector, but what we need is actually a matrix. So now we will use the reshape function from NumPy to reshape XGrid into a matrix where the number of lines is the number of elements of XGrid, that is len XGrid, and the number of columns, which is of course 1. And now, as you can see, if we execute this, XGrid will be a matrix of 1 column and 90 lines containing all the levels from 1 to 10 incremented by 0.1. Okay, so now let's of course replace X here by XGrid so that our model predicts all the salaries of these imaginary 90 levels from 1 to 10. And so now it's ready. Let's re-execute this. And here we go. You get a more continuous curve, which is actually the real curve of the polynomial regression itself. Alright, and now time to make the final prediction, and we'll actually do that in the next tutorial.